Hello students, we are going to learn today 2D transformations. In 2D transformations, we are going to learn what is translation, scaling, rotation, reflection, shearing. So let's see first what are transformations. Um, in 2D object, transformation is nothing but to change the object's either position, its size, its orientation, its shape, and reflection. Whenever we change this position of the object, then that kind of 2D transformation is called translation. When we are trying to change, when in particular transformation, if the size of the object is changed, then that is called scaling. Now, either the size of the object can be increased or it can be decreased. If the orientation of the object is changed, then in that case it is called rotation transformation. If the shape of the object is changed, then it is called shearing. And if reflection of the object is taken, if the mirror image of the object is taken, then it is called reflection transformation. So transformations play an important role in computer graphics to reposition the graphics on the screen and change their size and orientation. So it's very important topic in case of computer graphics. So transformation is process of modifying and repositioning the existing graphics. So there are various transformation techniques which I have just now explained, which from our syllabus, these 4 to 5 transformations are to be explained. First one is translation, rotation, then scaling, reflection, and shearing. First one we will see that is nothing but transformation. Sorry, that is nothing but 2D translation. So 2D translation is process of moving an object from one position to another in two-dimensional plane. So whenever we are mentioning two-dimensional plane, it means you'll have to consider x coordinates and y coordinates. So instead of talking about object, we will first talk about a point or a pixel. So consider a point object O that has to be moved from one position to another in 2D plane. So every point or that initial coordinate of that object or that point, you can see x and y. So x old and y old. Now, when the translation is to be applied or after applying 2D translation, the new coordinates of the object O after the translation will be x new and y new. So how can we get x new and y new from x old and y old? So to the x old, we need to add some parameter which will convert the x old into x new as well as x y old to y new. So the translation vector or the shift vector by which the object was translated or by which the point was translated, that is nothing but translation vector or shift vector. So that can be specified as tx and ty. So if you want to change the x coordinates to the x old, you'll have to add the tx so that you'll get the x new, as well as you'll have to add ty to the y old to get the y new. So, given a translation vector that is nothing but tx and ty, tx defines the distance the x old coordinate has to be moved, and ty defines the distance y old coordinate has to be moved. If you'll see the diagram, you can see x old and y old is specified with the point, and as we want to translate that black point by tx and ty, we'll have to add the tx to x old to get x new, whereas you'll have to add ty to y old to get y new. So this is how the translation can be performed. So this translation is achieved by adding the translation coordinates only. This is what I have explained right now. In matrix form, the above translation equation may be represented as like this. See, if we'll see, it is a matrix where you can have one column and two rows. X new, Y new equals to X old, Y old plus TX, TY. That is nothing but translation matrix. So if we want to use homogeneous coordinate representation, then in that case you'll have to add one more row, that is nothing but 1 to the matrix, that is nothing but translation matrix. So it will be 1 1 1 diagonally, whereas tx and ty is in the third column, and you will have to multiply it with the x old y old. to get the x new y new. So we'll see one practice problem which is related to 2D translation. It can be asked in exam for 4 to 5 marks. So given a circle with radius 10 and center coordinates 1, comma 4, apply the translation with distance 5 towards x-axis and 1 towards y-axis. Obtain the new coordinates of C without changing its radius. So in this problem, a circle is given whose radius is 10. The center coordinates of the circle are given. They are 1, comma 4. Now, as we need to translate the circle, but we need not have to change the shape of the circle. We just have to change the position of the circle. So the radius remains the same, but only the coordinates will change. But how the coordinates are to be translated? The translation vector is already given, or the shift vector is already given. So distance 5 towards x-axis. So we can consider tx as 5, whereas we can consider ty as 1. So the old center coordinates of C can be written as x old y old, that is nothing but 1, comma 4. Translation vector, which is nothing but tx comma ty, which can be written as 5, comma 1. And the new center coordinates of the circle can be written as x new is equal x new comma y new. So how can you get the new coordinates? That is nothing but x new is equal to x old plus tx, that is nothing but 1 plus 5, which is nothing but 6, and y new can be calculated as y old plus ty equals to 4 plus 1 4 plus 1 equals to 5. So the new center coordinates of C will be 6, comma 5. Here we can see that the earlier coordinates of the circle was 1, comma 4. Adding the shift vectors to these two values, we can get the new coordinate 6, comma 5, but the radius of the circle remains unchanged. So there is alternative way to do the same task to calculate the new center coordinates of C, where you can use this matrix where x new y new equals to x old y old plus tx ty. So x new y new is equal to 1, comma 4, that is nothing but your old coordinates, plus you can add the shift vectors, that is 5 plus 1. Here you can get easily by matrix addition 6, comma 5. Now second problem we can see for translation. A square is given with coordinates. As it is square, it will have 4 vertices. So the 4 vertices will be named as A, B, C, D. The coordinate points of A 0, 3, B 3, 3, C 3, 0, D 0, 0. Apply the translation with distance 1 towards x-axis and 1 towards y-axis. Obtain the new coordinates of the square. Here you can see that as tx and ty are given, tx is nothing but 1, whereas ty is also 1. So we want to apply translation to the square. Now instead of using circle, we are using object as square. So to this problem, you'll have to add this translation. Using the earlier problem, you can use the same thing here. How you can do that is you can consider A's coordinates 0, 3 as old coordinates. You can add 1 1 to it, so the new coordinates of A will be what? 1, 4, correct. As well as for B, the old coordinates are 3 3. To that 3 3 you can add 1 1, so the new coordinates of B will be 4 4. Similarly for C, old coordinates are 3 and 0. You can add 1 1 to it, it will become 4 1. And for D, old coordinates are 0 0. You can add 1 1 to it, so D's coordinates will become 1 1. So now you can easily draw the translated square. This was nothing but translation. The second transformation is nothing but 2D scaling. Now, as the name suggests, scaling means it is a process of modifying or altering the size of object. Not only increasing the size of the object, but you can also decrease the size of the object. So scaling may be used to increase or reduce the size of the object. Scaling subject to coordinate points of the original object to change. So here in case of scaling, you can consider point O, which is to be scaled in 2D plane. So initial coordinates of the point you can consider similar to the translation, that is x old y old. But here instead of translation vector, you'll have to use the scaling factor. So scaling factor for the x-axis can be called as Sx, whereas scaling factor for y-axis can be called as Sy. So the new coordinates of the object after scaling will be, of course, x new comma y new. But how to get this x new and y new? So here, instead of performing addition, which we used to perform in translation, here we can perform multiplication, where you can get the x new by multiplying x old with sx, whereas you can get y new by multiplying y old with sy. In the matrix form, you can write it like this: x new y new. It is a matrix where you can have one column and two rows, uh, equals to the scaling matrix, where you can use the scaling factors of x and y. You can multiply it with old coordinates, that is x old and y old. Now, if you want to convert the same equation, the matrix equation, to homogeneous coordinates, the above scaling matrix may be represented as 3 by 3 matrix, where you can add one more coordinate to the matrix, which will become now x new, y new, and 1. Matrix will become sx, xy, and the last one will be considered as 1, and multiplied with the x old, y old, and 1. This is just to convert the above equation into a homogeneous coordinate system. Now we'll consider problem regarding the scaling. Here the square is given, the same square: a 0, 3, b 3, 3, c 3, 0, d 0, 0. You'll have to apply the scaling values as sx equals to 2 and sy equals to 3, and obtain the new coordinates of the object. Now here in this case, the old coordinates of the square are given a, b, c, d. Scaling factors, that is nothing but sx is equal to 2, sy is equal to 3. Now we need to calculate a dash, that is x new, y new. For every point we need to calculate the new coordinates. So we will call those new points as a dash, b dash, c dash, and d dash. So a dash is nothing but x old into sx. So the earlier points were 0 and 3, no? So 0 into 2, that is nothing but sx. So 0 into 2 becomes 0, 3 into 3 becomes 9. Similarly, you can calculate a b dash, that is 3 into 0, 0, and 3 into 3, 9. Then similarly, you can calculate for c, that is 6, 0, which is after scaling, and d 0, 0, because earlier also it was 0, 0. So multiplying it with the scaling factors, it will become 0, 0 only. So if this is what the earlier square used to look like, after scaling, the size has increased. Why the size has increased? Because the sx and sy values are positive values. So that's why after scaling, the size of the object is increased. Now the next kind of transformation is nothing but 2D reflection. Reflection is kind of rotation, of course. Even if you are saying it is reflection, it is nothing but kind of rotating the object with 180-degree. So the reflected object is always formed on the other side of the mirror. So the size of the reflected object